Hello everyone, welcome back to the Simscope. Before we begin, I want to mention that I'm going to make a couple of these videos, which is of a detailed series I'm producing, and this couple of videos will not be a quick overview type of content. It will be deep technical breakdown suitable for anyone doing a final year project and either it can be a postgraduate research or industrial motor drive or something like that. So uh, across in this today's video, I will walk you through a Simulink model that uh, we will build a controller design for the PMSM, and finally we will see the results in the performance analysis. Specifically for the today's video, we focus on one thing, that is in the MATLAB we have a model where we are designing a controller for the PMSM motor. PMSM is a permanent magnet synchronous motor which gained its popularity over the decades for its high efficiency, higher torque density, and more highly precise control ability. So for simplification of this project, I have used surface mounted PMSM, and I have to control this motor. I have designed a robust sliding mode field based sliding mode control based field oriented controller, where for the PMSM, for the feedback type PMSM, the common controller is a field oriented controller, and the field oriented controller or FOC. So the FOC have a good control, fast response, and however when we add a load or due to the disturbances, the output we get at the load at the motor is varied, and there is a noise generated. So to reject that noise and make the motor control more robust, I'm adding a sliding mode control methods, and we will combine them together and make a sliding mode field oriented control hybrid. Now that was a brief overview. So firstly, moving on to a different level of structures I have in the model. I have my PMSM model here, which consists of a motors plant and plant model and inverter. Then I have a controller model. I have an input, I have an output, and input is usually the set points of reference speeds and the torque. So moving into the first subsystem, which says PMSM or motor, the plant model. This is a plant model. So it consists of a motor and an inverter. The DC battery, or it represents a Disturbance battery of a 300 Newton meter, a nominal voltage of a 300 volt with a rated capacity of 100 Ah is used here. It will feed the inverter, and the inverter converts the DC voltage into the AC 3-phase AC voltage, and it is feeding the PMSM motor. The PMSM motor that I have used is a 3-phase type, which will produce a back EMF of sinusoidal waveform, and the rotor type is round. Mechanical input is that I'm going to use is a torque, and the motor model I have selected has a rated torque of 6 Newton meter, nominal voltage of 300 volt, then rated speed of 4500 rpm. That means we are using a very high speed motor here. Oh, sorry. Next, the internal parameters of the motor. This is an important thing, especially for the PMSM controller. I'm going to upload the project reports, detailed equations, derivations, and how I have designed this controller is given in the project report, so you can go through my link and download the file. I'm going to upload the Simulink file with presentation videos and the final project report. So now moving back to the internal parameters of the motor, it has a stator resistance of 0.62 ohms, then its inductance is 2.07, so the armature inductance is 0.0020 millihenry, right? And the flux linkage is 0.08 Weber. Its inertia, viscous damping, pole pairs, static frictions are given here. Next is now the motor output is collected. Output of a motor is collected, and like a torque, then rotor angle, stator's IQ, voltage and current, and speed rotors are speed of a motor are collected using the different sensors of the motor. Now the rotor angle and the rotor speed are fed back to the controller, making the whole system a closed loop control system, and we have our speed and the rotor angle as a feedback in the feedback loop. Now, in case of the motor controller subcircuit, we are giving a reference speed from here, and it is feeding and given to the motor controller. The controller's output is a gate pulse, and this gate pulse is given to the inverter. This inverter, the gate pulse will control the inverter, and the power or the voltage generated by the inverter will be controlled based on the gate pulse, finally controlling the motor behavior. So inside the controller design, we have a field-oriented controller in combined with the sliding mode controller. Field-oriented controller block have a inner current loop, and the outer loop is a speed loop. This speed loop have a combined sliding mode controller. So The process for inside the controllers, firstly the current loop, we have a classic vector control sequence where three-phase current from the inverter is fed, and this current is given to the clock transformation to transform from a three-phase IABC to alpha beta domain. And after by using the angle theta and using the clock to park transformation or the park transformation, the alpha beta is components are converted to DQ components, and finally we are getting the components in the synchronous reference frame or DQ reference frame. That's where the field-oriented controller usually use D and Q axis control components to control. Now, I am using a surface-mounted PMSM motor here, and for the surface-mounted PMSM motor, the inductance L inductance and Q inductance are equal. Therefore, the torque is purely a function of a IQ. So that's why we have a ID reference as a 0, and the controller and by keeping this ID as a 0, we can also get a maximum torque per ampere. This is an inner loop, and it also have a PID controllers. It uses a PID controllers. This inner loop guarantees a precise torque and a flux control. Now, at the outer speed loop uses a sliding mode control speed controller, and it's technically a core the core technical controller for controlling the speed. We have an actual speed coming from here. I mean the reference speed or the set point speed, and the actual speed coming from here, and we are getting a error here. So in the sliding mode controller, the sliding surface has to be defined, which is defined by this sigma is equals to lambda E can be error plus differential of derivatives of the error. So lambda times E or lambda times E plus derivative of error, and by defining that one, we are defining the sliding surface. Now, where E is a speed tracking error, and when usually we say that we use a signal function to in the sliding mode controller to control the speed. However, we are replacing the signal function with the relay function to create the hysteresis band of plus or minus 0.14, and this allows certain hysteresis band. Why do we replace the signal function? This signal function, the sliding mode traditionally uses the signal function. However, the signal function causes very high chattering. It causes a chattering due to its high frequency of switching, and therefore, instead of using the signal function, we used a relay, and it dramatically reduces the switching ripples. Now, after calculating all the values using the lot of formulas and equations, I've got my lambda 60. Then these are the 2 values of the SMC, and this gives the good results for the specifically for the motor selected, the motor that I have selected. And finally, I am getting an IQ. This IQ is a current command. We call it as a current command, and SMC outputs generate IQ. In case of the inner current loop, it will produce ID dash, and these signals are then given to the Park to Clark transformation. Now this is an inverse transformation where we are giving a TQ components and we are getting an output in the alpha beta domain. And using the SVPWM generator level 2, it will generate the PWM pulse that will be finally used to which is connected to the gate of the inverter, and it will control the inverter and the motor. This is a very complete explanation of the model. So we can see that we have a closed loop, and now we will perform different tests. It's the topology is very clear. We have a speed reference entering the SMC, then the SMC will compute IQ, then FOC will enforce the IQ and ID behaviors, then SVPM or the PWM generator will control the inverter, then motor will respond, and measurements feedback into the loop. This structure enables stable, we can say that it will produce a stable control even under the sudden disturbances or high dynamic variations. So if we keep suddenly a very large load, or if there is a disturbances, yeah, it should work. Now, to analyze the performance of this designed controller, we are going to perform 4 different tests. One is a step response test, second is a load disturbance test, third is a speed reversal test, and fourth is a sinusoidal tracking test. Let's go with the first, the step response test. Now in the step response test, we are going to keep the rated torque or the load torque at 0. So we are running at a no load, and we will increase our speed from 0 to 2700. So around 60% of the rated speed at time 0.3 seconds. You can generally compute the dq axis voltage and dq axis current from here. Then you can get an output current and voltage, I mean the speed and the torques, and the inverter voltages from here. Now in the step response test, controller is taking the motor speed, and it is taking the motor control from 0 to 2700 rpm. we are giving we are going to use this scope, and we are feeding the reference speed, the actual speed, and the torque. The first order filter is used to filter the torque because it has a high ripple. Now firstly I have a speed, and second waveform is a torque waveform. The torque is very simple. Since we have kept the torque as a 0, it at a steady state it's trying to keep it at 0, maintain a 0 torque. However, you can see it's moving from around 0.3, the maximum should be 0.25 to negative 0.05. Yeah, negative 0.15. So it is trying to maintain the torque at the 0, and at the time 0.3 we have the speed. Yellow is a reference speed. The reference motor is initially running not started, so at the time 0.3 when we start the motor, we have already set the motor speed to 2700. Therefore, the reference speed yellow is moved to 2700. Now the blue waveform is an actual speed, actual waveform or the actual speed, and it should follow the reference speed. Now we can say that at this transient we can say that the actual speed of the motor is following the set point or the reference speed. It is rising at the rising time of 8 milliseconds. There is no overshoot, and settling time is very small, around 0.02 seconds, right? It's around 0.02 seconds. So this matches this waveform shows a critical damping behavior of the motor, and it confirms that the sliding mode controller controls the speed of a motor precisely. If we go and look, if we zoom and look into the actual speed at the steady state, you can still see some chattering. The chattering is still there, and we cannot completely remove it. This chattering band is around 2698 to 2700 RPM, which is expected due to the hysteresis control. However, if we are using the signum function instead of a relay function, chattering is very large. This is the first step response test. Now next, let's conduct load disturbance test. Now, what is a load disturbance test? We will run the speed at 2700 constant speed, and we will now introduce the load. The rated load of the motor is 6 Newton meter. So now we are going to, firstly we will run at an underload of 3 Newton meter. So we can see that the motor is running at the underload of 3 Newton meter, 50% underload, 50% loaded condition, and that is introduced at the time of 0.5 seconds. Okay. This test can be I have conducted 3 different tests at the underload condition, at the rated loaded condition, and overloaded condition. Usually the rated and underload condition behavior at the waveform, it produces almost a similar behavior. However, in case of the overloaded condition, there is some variation. In this video, I am trying to make the video short, so I will only show you how we conduct the underloaded condition of 50% rated load and explain its waveform. You can change the rated speed to the torque to 6 Newton meter and greater than 6 Newton meter to understand the behavior of overload and rated loaded conditions. Now this is at the 3 Newton meter torque. Now you can see that the motor is initially not off. Initially it was off, and at the time 0.3 we are turning on the motor and we are setting the motor speed at 2700 rpm constantly throughout the process. And while doing that, if you observe the torque waveform, and there is a sudden spike of a torque at around maximum of 11 Newton meter, and this is due to as the motor was initially at the zero speed. When we suddenly increase to the 2700, it requires a very high torque to increase the motor or ramp up the motor speed to 0 to 2700. Therefore, we are getting this waveform here. Now once the motor is running at 2700 stable speed, at the time 0.5 I am adding a load of 3 Newton meter, and you can see that my load waveforms are shown here. However, if you zoom out and see the waveform of a speed at the transient mode, when the speed was increased, you can see the steep actual speed dip of 12 rpm, and this is equivalent to plus or minus 2%. So the actual speed when the torque is increased, the motor speed decreases and it reaches to 2600. So this happens during the transient mode, and it should be minimum. This is not what we want. So therefore the SMC or the controller will control and should recover this speed dip, and it does recover within a 0.02 seconds, around 0.02 seconds then. And the torque response shows a very clean and compensate with the torque ripple of, we can say, plus or minus 0.15 Newton meters approximately. Now, what does this test shows or proves? This proves that excellent disturbance rejection uh, and torque stability of the controller. Let's perform the next test, which is a speed reversal test. Now, in case of a speed reversal test, we are going to flip the speed of the motor from 2700 to minus 2700. So what we are trying to do is we are just saying that, and we will keep the motor, let's run at the no load torque, and we are trying to demonstrate the bidirectional control of the controller, bidirectional control of the motor. The motor should turn clockwise or anti-clockwise, so we are trying to prove that using the speed reversal test. In the loaded condition also, the behavior should be same for this reversal test. Now let's see the waveforms. Okay, very nice. Initially, when we start the motor, the speed is increased to positive 2700 and the motor is running at the 2700 rpm. Now at the time 0.3 seconds, now we are reversing the motor direction, reversing the motor direction, and if you can see that my set point is here and it reaches to negative 2700 and the motor actual speed also reverses and reaches negative 2700 rpm. It is crossing the zero smoothly. When we reverse the direction of the motor, it settled within 30 to 40 milliseconds, and you can also see that the torque is flipped. If we are running at the no load torque, if we run at the loaded conditions, it will flip. So this demonstrates a strong bidirectional control with a high stable control system. Okay, and finally the last is a sinusoidal tracking test. For the sinusoidal tracking test, what we are going to do is we are taking an sinusoidal waveform as a reference speed, and the actual speed should track that sinusoidal waveform. So to do that, we are giving an amplitude of 81, again the bias of 2700 rpm, and the frequency for the sinusoidal wave should be 31.4 and its sample time is 0. Again running at a no load. This should be the final test. Okay, let's raise our sinusoidal waveform. Okay, you can see that the yellow line is our sinusoidal reference speed, and the actual motor speed increases from 0 to 2700, and it is tracking the reference speed exactly. However, if we zoom in and see the actual speed at the stable state, we can also see the chattering here. So the motor, we can, from using this test, we can say that the motor has tracked its reference speed perfectly with only a minor phase lag, and the tracking accuracy remained high, confirming a robust under continuous dynamic excitation. Okay. To summarize the whole project, we can say that the SMC FOC hybrid controller is working well. It has a rising time of 8 milliseconds, no overshoot. Good. And a very fast reversal response. So the controller ability to deliver a high performance, or ability to control the PMSM, is robust and superior. And if you compare this with SMC FOC hybrid with only the FOC controller, its trend will be higher, or its behavior will be more better than the FOC controller. Now, to conclude, we have gone through the Simulink model, and we have conducted how the various different tests. And before finishing this video, I would like to say that the voltage and the torque equation, the mathematical equation, and the derivation of voltage equation and the torque equation is implemented in this subsystem of PMSM, and all the motor parameters are defined by the motor controller. Okay, thank you for watching. I'm going to upload all the MATLAB file, project reports. I have also made a presentation video that I have presented to the panel members, but I'm not going to upload the presentation video in the YouTube. However, I will upload that in a Gumroad. Please check my link. You can find all the necessary documents and project related documents in the Gumroad. You can download from there and refer for your project. Thank you so much.